Most people remember the moon landing. The harder part was getting home. Once Apollo touched down, the crew still had to launch off the moon, find their way back to the command module, cross deep space and survive re-entry, all with almost no room for error. The moon was not just a place they visited, it was a place that could trap them. Yes, lunar gravity is much weaker than Earth's, about 1.62 meters per second squared, or about 5.3 feet per second squared, around 1/6 of Earth gravity. But weaker does not mean harmless. To get home, you still have to launch from the moon, reach orbit around the moon, and do it from a world with no air, no runway, no rescue aircraft, no backup launch pad, and no second vehicle waiting nearby. Even the moon's escape velocity is about 2.38 kilometers per second, around 5,300 miles per hour, so the basic problem was already severe. It was not enough to land there. They had to prove they could leave, and that is where the real achievement starts to look different. NASA did not treat coming home as something separate from landing. The whole mission was built around the return from the beginning. If there was no reliable way to get 2 astronauts off the surface and back to the 3rd astronaut waiting in orbit, then the landing itself had no value. That is why Apollo was designed around lunar orbit rendezvous. A small spacecraft would go down to the surface. A second spacecraft would stay in orbit around the moon, and only the command module, not the lander, would come all the way back to Earth. That decision sounds simple now, but it shaped everything. NASA was not designing a moon trip, NASA was designing a complete chain of survival. The landing had to fit inside that chain. The moonwalk had to fit inside that chain. The science, the cameras, the samples, all of it only mattered if the architecture could carry the crew back in stages. So even before Apollo 11 ever launched, the return problem had already decided what kind of spacecraft they would build, how much mass they could carry, and how every major maneuver would work. Then you look at the timeline and the pressure becomes very clear. Armstrong and Aldrin were on the lunar surface for 21 hours and 36 minutes. That sounds like a decent amount of time until you realise how little slack they actually had. Their stay was tightly tied to power, life support, consumables, launch timing, and orbital mechanics. They could not just leave whenever they wanted. Their ascent stage, the upper half of the lunar module, had to launch at the right time to meet Columbia, the command module, where Michael Collins was orbiting the moon alone. On Apollo 11, the ascent engine ignited at 124 hours, 22 minutes mission elapsed time. Then it burned for 435 seconds, a little over 7 minutes, to get them back into lunar orbit. That burn was not a rough push upward. It had to place them on the right path, at the right speed, in the right orbital relationship to Collins. If that ascent failed, there was no rescue mission coming. If the engine did not light, the mission ended on the moon. If the burn was badly wrong, they might reach a useless orbit or not reach orbit at all. So when people remember the first steps on the moon, they are often remembering the most famous moment, not the most dangerous dependency. Then comes the next uncomfortable fact. Launching off the moon still did not mean they were safe. They still had to dock with Columbia. On Apollo 11, docking happened at 128 hours, 3 minutes into the mission. That moment matters more than most people realise. Until Rendezvous succeeded, Armstrong and Aldrin were still in a spacecraft that could not bring them back to Earth. The lunar module ascent stage was built to get them off the surface and into orbit. It was not built for Earth re-entry. It was not built to survive the return through Earth's atmosphere. So the mission only started to become survivable again after they reunited with Collins and got back into the command module. That changes the emotional shape of the whole mission. The famous landing is usually treated as the climax. In reality, from a survival point of view, Apollo still had multiple critical gates after the moonwalk was over. First, they had to get off the surface. Then they had to rebuild the mission in orbit by rendezvousing and docking. Then they had to prepare for the burn that would send them back toward Earth. So even after the moon landing succeeded, the crew was still moving through a sequence where any major failure could still kill them. And even then, after docking, they still were not home. This is another place where popular memory compresses everything into one simple idea. People hear they left the moon, and it sounds like the return was basically done. it was not. Apollo 11 still needed a trans-Earth injection burn to leave lunar orbit and aim back toward Earth. Then it needed a mid-course correction during the trip home. Then it needed to survive atmospheric entry at lunar return speed. Then it needed parachute deployment. Then it needed a controlled splashdown in the Pacific where the recovery forces could reach them. Apollo 11 finally landed in the ocean after 195 hours, 18 minutes and 35 seconds of total mission time, about 13 miles from USS Hornet. So the word return hides a lot. It sounds like one action, but it was really a chain. Surface departure, orbital insertion, rendezvous, docking, transfer, lunar departure, coast home, entry, parachute, splashdown, recovery. Every one of those steps had its own systems, timing and failure modes. A problem in any one of them could still end the mission. That is why the return from the moon was not one dramatic moment. It was a long sequence of technical wins that had to happen in order, and that is the first thing you need to understand before the rest of Apollo makes sense. The moon landing was not the point where the mission became safe. It was the point where a different set of risks took over. NASA's real challenge was not just putting people on the moon, it was designing a mission where the landing could turn into a round trip. That required spacecraft built for different jobs, precise timing, and almost no wasted margin. So the obvious next question is the one NASA had to answer early. If bringing one giant spacecraft down to the moon and then back to Earth was too heavy and too risky, then how did they solve it? How did they make the return physically possible without trying to make one vehicle do everything? The obvious plan sounds like the safest one, and that is exactly why it was so dangerous. If you know a crew has to land on the moon and then come back to Earth, your first instinct is simple. Build one big ship, land the whole thing, and then launch the whole thing home again. No meeting in orbit, no separating into different vehicles, no crew split, no need to reconnect the mission later. On paper, that sounds cleaner, sounds safer, sounds like fewer moving parts, but in Apollo, that obvious idea was the wrong idea. The reason is mass, and mass is where spaceflight gets brutal very quickly. If you try to land a full Earth return spacecraft on the moon, that spacecraft has to carry everything needed for the trip home all the way down to the surface and then lift all of that back up again. That means a larger vehicle, more fuel, larger engines, stronger structure, and then even more fuel to carry that extra fuel. Every kilogram creates a penalty because you have to accelerate it, support it, and design around it. In imperial terms, every extra pound keeps multiplying into more pounds somewhere else. That is why these missions are not just about building a powerful rocket. They are about not carrying what you do not absolutely need. And this is where the logic starts to turn. A giant all-in-one moonship does not become safer as it gets bigger. It becomes harder to launch from Earth, harder to land on the moon, and harder to launch back off the moon. The full Earth return hardware would have to survive every stage of the mission, including the descent to the surface, even though most of it was only needed later. That is terrible design if your real problem is just getting two people down and then back up again. NASA understood that the moon punishes unnecessary mass. If you bring too much machine to the surface starts owning you. So in 1962, NASA made the decision that changed the entire mission. Instead of direct ascent, they chose lunar orbit rendezvous. That meant one spacecraft would stay in orbit around the moon while a much smaller lander went down to the surface. Then the lander would come back up, meet the mothership again, and only the command module would return to Earth. That choice is the reason Apollo became physically possible in the Saturn V era. Without it, the amount of mass involved becomes so severe that the entire mission starts pushing beyond practical limits. Now, that does not mean lunar orbit rendezvous was some neat, elegant solution with no downside. It solved one problem by creating another one, and the new one was emotionally much worse. Once NASA split the job in half, they also split the crew. 2 astronauts would go down to the lunar surface in one vehicle. The third would stay alone in lunar orbit in another. That means the return path now depends on separation, timing, and reconnection. If the lunar module cannot relaunch, nobody comes to get them. If the ascent stage reaches orbit but misses rendezvous, they still cannot come home. If the command module has a problem while orbiting alone, the entire chain breaks in a different place. So yes, lunar orbit rendezvous saved mass, but it also hardwired one of the coldest failure modes in all of human exploration. You are close enough to see home as a direction, but too far for anyone to rescue you. That is the trade Apollo accepted. It did not remove danger. It concentrated danger into specific moments and then tried to engineer those moments so precisely that the crew could survive them. And that is why Apollo looks so bold even now. NASA did not choose the architecture that felt emotionally safe. NASA chose the one that the physics would actually allow, and the reward for that decision was enormous. Because only the command module had to survive Earth re-entry, NASA did not have to force the lunar lander to be good at jobs it would never perform. The lunar module did not need an aerodynamic shape because it would never fly through air. It did not need a heat shield because it would never re-enter Earth's atmosphere. It did not need wings, streamlining, or ocean landing hardware. It did not need to be pretty, stable in wind, or useful in any environment except vacuum and lunar gravity. It only had to do 3 things: go down to the moon, stay alive there for a short time, and then get back up into orbit. That is why the LM looks so strange. It looks fragile, angular, and almost unfinished because it was designed with ruthless focus. It was not trying to be a general spacecraft. It was a highly specialized machine, and that specialization is what made the whole return chain manageable. Instead of asking one vehicle to do everything, Apollo turned the mission into a series of smaller physics problems. One spacecraft handled deep space travel and Earth return. Another handled lunar landing and lunar ascent. That sounds less dramatic than a single giant moonship, but it is far smarter. This is the part where the story gets more direct. Apollo got home because NASA stopped trying to make one heroic machine do every job. They split the mission into 2 machines with 2 very different purposes. One spacecraft was built to live in vacuum, touch the moon, and launch from the moon. The other was built to stay in space longer, carry the crew through cislunar space, and survive a return to Earth at about 39,000 kilometers per hour, around 24,000 miles per hour. Those are not similar jobs. They pull design in different directions. Trying to merge them into one vehicle sounds clean, but in reality it makes the vehicle worse at everything important. And there is a bigger lesson inside that. People often think the smartest engineering solution is the one that looks simplest from the outside. In Apollo, that was not true. The smartest solution looked more complicated because it involved multiple spacecraft, multiple dockings, multiple separations, and a crew split across different vehicles. But underneath that complexity, it was actually cleaner in the only way that mattered. Each machine did a smaller number of jobs, and each kilogram had a reason to exist. That is why mass ratios mattered so much. NASA was not chasing elegance in the visual sense. They were chasing a design where the numbers closed, where the rocket could lift the hardware, where the lander could touch down without carrying dead weight, where the ascent stages could get back to orbit without hauling an Earth heat shield it would never use, and where the command module could stay protected for the one part of the mission that no other vehicle could survive. Apollo got home because the system was divided according to physics, not according to what looked emotionally comfortable. But that also makes the risk feel sharper. The same architecture that made Apollo possible also made it unforgiving. Once 2 astronauts went down to the surface, they were trusting a separate vehicle to lift them back into lunar orbit and reconnect them with the only spacecraft that could actually bring them home. NASA had solved the mass problem, but in doing that, they had also created a mission where rejoining in lunar orbit was no longer optional, it was everything. And that leads straight to the next question. If the lander did not need to be a full spaceship, if it was never meant to fly through air or come back to Earth, then what exactly was it? What kind of machine do you build when its only purpose is to keep 2 astronauts from being stranded on the moon? The lunar module was not a normal spacecraft, and that is exactly why it worked. If you look at it expecting a polished ship built to travel everywhere, it makes no sense. It looks awkward, thin, and exposed. But that is because the LM was never meant to do everything. It had one purpose: keep 2 astronauts from being stranded on the moon. That is the right way to think about it. It was not a moon cruiser. It was a machine built to get 2 people down to the surface and then get them back off before the moon kept them there. That is why the LM was split into 2 major parts. The descent stage handled the landing. It had the landing gear, the descent engine, and the structure that actually touched the lunar surface. And once the landing was done, that lower half had finished most of its job. It stayed behind on the moon and became the launch platform for the upper half. The ascent stage was the part that really mattered for survival after the moonwalk. That was the section with the crew cabin, the controls, and the engine that had to fire to lift Armstrong and Aldrin back into orbit. So the lunar module was not one unified return vehicle. It was a temporary system that shed part of itself the moment that part was no longer useful. And that explains why it looked so strange. It was never designed to fly in air, so it did not need smooth lines or aerodynamic stability. It was never meant to land on Earth, so it did not need a heat shield, parachutes, or an ocean recovery structure. It was never meant to come all the way home, so it did not need the kind of protection or versatility a full spacecraft would need. Every part of it was shaped by a very narrow question. What is the minimum machine that can land on the moon, support 2 people briefly, and then launch them back into lunar orbit? That kind of design sounds efficient, and it was, but it also means the LM carried no comfort margin in the usual sense. There was no extra ability hidden inside it to save the day in some new scenario. It was specialized because it had to be. And when you design that tightly, one engine starts to matter more than almost anything else in the mission. That engine was the ascent engine. On paper, its thrust does not sound huge, about 3,500 pounds of thrust, around 15.6 kilonewtons. If you compare that to major launch vehicles, it seems almost small, but that comparison misses the point. This engine was not trying to lift a giant rocket through thick atmosphere under Earth gravity. It was working in vacuum, under lunar gravity, lifting a stripped-down upper stage that had already left most of its dead weight behind on the surface. In that environment, that engine was enough. More importantly, it had to be enough the first time. And this is where the mission gets hard to soften. There was no engine out mode, there was no second ascent engine waiting in parallel, there was no rescue ship that could come down and pick them up if the engine failed. If that engine did not light, Armstrong and Aldrin stayed on the moon. If it started and then failed badly, the result was not some damaged mission with a delayed recovery. The result was 2 astronauts trapped on another world. So that one engine, small by rocket standards, was the line between a successful moon landing and a permanent burial site. That is also why NASA did not trust a single path of guidance and control. The LM carried its main guidance, navigation and control system, but it also carried a separate abort guidance system. The backup system was not as capable as the primary one, but that was not the point. The point was survival. During descent, ascent, or rendezvous, NASA wanted another independent way to keep the mission from collapsing if something went wrong in the main chain. When your whole architecture depends on relaunching from the moon and finding another spacecraft in orbit, you do not treat redundancy as a luxury. You treat it as basic survival planning. And that tells you something important about Apollo engineering. NASA was not pretending the system was fail-proof. They knew exactly where the dangerous points were. They knew ascent was unforgiving. They knew rendezvous was unforgiving, so instead of hoping the primary system would always behave, they built a backup path for the moments where one bad failure could end the mission. Not a perfect backup, not a magical backup, but something independent enough to matter. Then there is the part that sounds almost absurd now. The computers doing this work were tiny by modern standards. Apollo's guidance computer had 36,864 words of fixed memory and 2,048 words of erasable memory. That is microscopic compared with modern devices. A cheap smartwatch, a basic calculator-like gadget, even ordinary household electronics can look powerful next to that. But the important point is not that Apollo succeeded with weak computers. The important point is that Apollo was designed so carefully that those computers could do the job. The computer did not need to behave like a modern machine running giant software stacks. It needed to do a very disciplined set of tasks, navigation support, engine control, attitude control, rendezvous logic, and crew interface in real time. That is still a serious workload, and it had to do it under conditions where mistakes were expensive. The mission got away with limited computing power because the vehicle design, the procedures, the crew training, and the flight plan were all simplified as much as possible around that limit. That is one of the least appreciated truths about Apollo. It did not get home because the onboard computers were overwhelmingly powerful. It got home because the mission was engineered cleanly enough that limited computers could still manage it. The hardware, the software, and the operations all fit together tightly. NASA was not throwing technology at the problem in the modern sense. NASA was narrowing the problem until the available technology could handle it. And when you put all of that together, the lunar module starts to look less like a spacecraft and more like exactly what it really was, a disposable escape machine. The descent stage got them to the surface and then stayed behind forever. The ascent stage existed to do one critical thing: lift them off the moon and put them back on a path toward Columbia. The guidance system existed to support that climb and the rendezvous after it. The computer existed to run a tightly controlled sequence with almost no room for confusion. Nothing in that design was broad, elegant, or general purpose. It was all focused on one problem: do not leave these people stuck on the moon. And that focus is what makes the next step feel even harsher. Once the moonwalk was over, once the samples were packed and the surface work was done, there was no gradual exit, no runway takeoff, no second attempt if something felt wrong. At some point they had to ignite that ascent engine and commit. So the next real question is not just how the LM was built. The next question is what it meant to actually launch off the moon, when one burn had to turn a landing site into a departure point, and there was no pause button once it started. Launching off the moon was the most irreversible moment of the mission, because once that engine lit, there was nothing left to negotiate. On Earth, a launch can sometimes be delayed, recycled, or stopped before it fully commits. Weather can interfere, a valve can misbehave, a countdown can pause, and the crew can still be on a pad with ground support around them. None of that existed on the moon. Armstrong and Aldrin were sitting in the ascent stage on top of the discarded descent stage, on an airless surface, with one ascent engine and a launch time set by orbital mechanics. They were not waiting for good conditions, they were waiting for the exact moment when a spacecraft moving above the moon could still be reached. So when the ascent engine ignited, this was not takeoff in the normal sense. It was not like a plane leaving a runway, and it was not even like a normal rocket launch from Earth. It was a timed insertion into a moving geometry problem. The command module was already in orbit, moving fast around the moon, with Michael Collins inside. Armstrong and Aldrin had to launch in a way that would place them into the right orbital relationship to meet him later. That means ignition was not just the start of flight, it was the start of a commitment. Once they lit that engine, the mission moved onto a path that had to work, and the numbers show how tight that commitment really was. Apollo 11's ascent engine burned for 435 seconds, a little more than 7 minutes. In that short time, it had to lift the ascent stage off the moon and place it into an initial orbit of about 11 by 55 miles or 18 by 89 kilometers. That sounds straightforward until you realize what that burn had to do all at once. It had to build the right speed. It had to happen at the right time. It had to put them in the right orbital plane relative to Columbia. And it had to do all of that with a vehicle that had no real backup if the burn was seriously wrong. This is where people can underestimate the danger, because the moon seems simpler than Earth. There is no weather, no atmosphere, no wind shear, no storm system, no thick air pushing against the vehicle. That sounds helpful, and in some ways it is, but the same simplicity also removes anything that might soften your errors. A bad launch from Earth can still sometimes end with ocean recovery, emergency procedures, or at least some margin created by atmosphere and range safety systems. A bad launch from the moon does not give you those kinds of outcomes. You can miss the intended orbit, you can end up in an orbit that is useless for rendezvous, or you can wind up on a path that brings you back down to the surface. So yes, the moon's gravity is lower, and that absolutely helped. It takes less energy to lift off there than it does from Earth. But low gravity can create a false sense of ease if you say it too casually. Easier is not easy. The moon has no atmosphere, and that means there is no aerodynamic lift, no air resistance to work with, no wings, no gliding, no way to shape your path except with rocket thrust and attitude control. On Earth, flight can sometimes hide part of the problem inside air. On the moon, there is nowhere to hide. Everything is pure rocket performance. You either carry the speed change you need, or you do not get home. That is why lunar launch was so unforgiving. There was no extra system that could compensate for a major shortfall. There was no atmosphere to help stabilize a weak ascent. There was no chance to circle around and try again from a runway. The ascent stage had to rise, accelerate and enter the intended orbit using exactly the energy and guidance the mission had planned for. In a way that makes the moon more direct than Earth. It does not disguise mistakes, it shows them immediately. And this is where Apollo's design becomes both smart and severe at the same time. The descent stage stayed on the moon forever. The ascent stage separated from it, rose into space, and for a short time became its own tiny spacecraft. That transition is one of the cleanest ideas in the whole mission. Once a piece of hardware had done its job, Apollo abandoned it. The landing stage got them down, so it was left behind. The ascent stage got them back into orbit, but it would not be needed forever either. The mission came home by shedding hardware again and again, keeping only what still served survival. That is a very different logic from the way people usually picture space missions. A lot of people assume success means preserving the vehicle and bringing as much of it back as possible. Apollo did almost the opposite. Success meant dropping every piece that was no longer necessary, because carrying dead weight makes the next step harder. The return from the moon worked because NASA was willing to treat spacecraft as temporary tools, not sacred machines that had to stay together. And that is why launching off the moon feels so final when you look at it closely. The moonwalk was over. The surface work was over. The descent stage had become a piece of abandoned hardware on another world. The astronauts were now in the smallest possible vehicle that could still save them. And that vehicle had one task left: get into lunar orbit and meet Columbia. There was no benefit in delay. There was no safety in waiting. There was only the exact burn they had trained for at the exact time they needed. This is also the moment where the return stops looking like one long trip and starts looking like a chain of separate survivals. First, they had survived the landing. Then they survived the stay on the surface. Then they survived ignition and ascent. But even after that burn was complete, they were still not in the safe ship. They were only in lunar orbit in a temporary spacecraft trying to reconnect with the one vehicle that could actually cross this lunar space and survive Earth re-entry. So the next step was even stranger than most people realise. After they launched off the moon, they did not point straight at Earth. They could not. Earth was not the first destination. The first destination was Michael Collins, circling above them in Columbia. And in orbital mechanics, finding somebody is a lot harder than just flying toward them. They did not go back to Earth first, and that is one of the most important things to understand. After Armstrong and Aldrin launched off the moon, they were still not in the spacecraft that could actually bring them home. The safe ship was still Columbia, with Michael Collins alone inside, circling in lunar orbit. So the first destination after liftoff was not Earth. It was rendezvous. That changes the whole picture. People often compress the story and think the astronauts left the moon and then headed home. That is not what happened. First, the ascent stage had to reach an initial orbit around the moon. Then it had to reshape that orbit so it could line up with the command module. On Apollo 11, the lunar module first got into an orbit near 56 miles, about 90 kilometers altitude. After that, more adjustments refined the path to roughly 57 by 72 miles, or about 92 by 116 kilometers, before docking. So even after a successful launch from the moon, Armstrong and Aldrin were still in a temporary spacecraft doing orbital setup work, not returning to Earth. And this is where the problem becomes less intuitive. Rendezvous in orbit is not the same as flying towards something in a straight line. In everyday life, if you want to catch someone, you point yourself at them and move closer. In orbit, that can make you miss. Orbital mechanics does not behave the way your instincts expect. If you fire your engines the wrong way at the wrong time, you do not simply move closer, you change your orbit, which changes where you will be later, and how fast you will be moving relative to the other spacecraft later. So the real job was not to chase Columbia directly. The real job was to enter the correct sequence of orbits so that both spacecraft arrived at the same place at the same time with manageable relative speed. That is why rendezvous planning became its own technical field during Apollo. The key was not just speed, it was timing, altitude, geometry, and phasing. One burn might raise part of the orbit. Another might circularize it. Another might change the timing of arrival. Another might reduce the closing speed. Every maneuver changed the future relationship between the two spacecraft. So when the lunar module was hunting down Columbia, it was not doing something that looked like pursuit in the ordinary sense. It was solving a moving geometry problem in real time. And that matters because Armstrong and Aldrin were still living inside the consequences of every earlier decision. The LM was good at short-term work in vacuum and lunar gravity, but it was not a long-range return vehicle. It could not survive Earth re-entry, it was not built for that. So if rendezvous failed, they were not just delayed, they were stranded in lunar space in the wrong spacecraft. That is why this step carries so much tension once you strip away the familiar Apollo imagery. Launching off the moon solved only one problem. It did not solve the main one yet. This is also why the rendezvous hardware had to be taken seriously. Relative motion in orbit is everything. You need to know how far away the target is, how fast the distance is changing, and how your line of sight is shifting. The lunar module had rendezvous radar for exactly that reason. It could measure range rate, and line of sight angles, and NASA documentation gives it an operating range from 80 feet to 486 nautical miles. That is a huge range span, and it shows the radar was not just for the final close-in moments. It supported the whole process of finding, tracking, and approaching the command module in lunar orbit. And NASA did not stop there. The command and service module also carried a VHF ranging device as a backup to the lunar module's rendezvous radar. That backup tells you how seriously this step was treated. Earth return depended on a successful meeting in lunar orbit, so NASA built a backup chain into the meeting itself. That is a pattern you see again and again in Apollo. The most dangerous steps were not left to one piece of hardware if a second path could be added. But even with radar and backups, there was still another fact that people often miss. Michael Collins was not parked somewhere waiting in a fixed spot. Columbia was moving around the moon at orbital speed. Collins had to maintain the right orbit, manage his own spacecraft, stay prepared for the rendezvous sequence, and be ready to support docking when the lunar module came up from the surface. He was not a passive part of the mission. He was preserving the only spacecraft that could survive the return to Earth. That point matters because Apollo mythology often isolates the moonwalkers and leaves Collins in the background. But the return home made his role central. While Armstrong and Aldrin were on the surface, Collins was effectively holding custody of the mission's only true Earth return vehicle. If his orbit had been wrong, if Columbia had suffered a major problem, if he had not been where he needed to be when the lunar module came up, then the return chain would have broken there instead. So the mission after lunar liftoff was not just about the two astronauts who had walked on the moon, it was about reuniting the whole architecture. The lander had done its job by getting two people off the surface. Now it had to reconnect with the command module, because that was the only way the moon mission could become an Earth return mission again. And that is what makes lunar orbit rendezvous one of the hardest parts of Apollo to feel properly. It sounds procedural when you summarize it. Reach orbit, adjust orbit, dock. But underneath those words, the situation is severe. Two astronauts are in a temporary spacecraft that cannot bring them home. A third astronaut is circling alone in the only spacecraft that can. Both vehicles are moving fast around another world. And the only path back to Earth is for them to meet correctly in lunar orbit. So when people say Apollo came back from the moon, that sentence hides this entire phase. They did not simply leave the surface and head home. They had to find the safe ship first. They had to rebuild the mission in space before they could even think about Earth. And that makes the next moment even more important, because once docking finally happened, the mission changed shape again. That was the point when 2 astronauts stopped depending on a disposable ascent stage and got back inside the one spacecraft that could survive the trip home. In other words, docking in lunar orbit was the moment the mission became survivable again. Docking sounds routine now only because Apollo made it look routine. At the time, it was not some final tidy step after the exciting part. It was the point where 2 astronauts stopped depending on a temporary escape vehicle and got back into the only spacecraft that could actually carry them to Earth. On Apollo 11, docking happened at 128 hours, 3 minutes into the mission. That number should matter more than it usually does, because it marks the moment the mission became survivable again in the full sense. Until then, Armstrong and Aldrin had escaped the moon's surface, but they were still not safe. They were still in a vehicle that could not survive Earth return. That is the key thing. Launching off the moon was essential, but it was not enough. Reaching lunar orbit was essential, but still not enough. The mission only changed from temporary survival to possible return when the lunar module and the command module came together and locked as one combined system. Before that, the margin was still very thin. After that, for the first time since the descent to the moon began, all 3 astronauts were back in the return architecture that had been designed to bring them home. And the docking itself was not just one clean click. Apollo's docking system had to do several jobs in order. First, it had to align the 2 spacecraft correctly. Then it had to capture them gently enough to control the relative motion. That was the soft dock phase. After that, the system had to pull the vehicles into a firm structural connection, a hard dock, where the connection was rigid, sealed, and strong enough for transfer operations. That distinction matters because docking was not symbolic. It had to become mechanically real. If the seal was wrong, if alignment was incomplete, if the structural connection was not secure, then the astronauts still could not move safely between the spacecraft. And once that hard dock was complete, the next part of getting home began immediately. Armstrong and Aldrin did not just climb back into Columbia empty-handed. They had to transfer themselves, the lunar samples, exposed film, checklists, and mission data. That is easy to rush past, but it matters. The moon mission was not only about surviving, it was also about bringing back evidence, geology, photography, and records of what had happened on the surface. If you do not bring those things home, then part of the mission's value is lost. So even at this late stage, after launch and rendezvous and docking, the crew still had to physically move the results of the landing from one spacecraft to the other. That also tells you how NASA thought about success. Getting home did not only mean saving the astronauts, it meant returning the astronauts and the proof of what they had done. The samples mattered, the film mattered, the notes mattered, the procedures did not stop just because the hardest orbital work was over. Apollo return was still an organised transfer from one stage of the mission to the next. And then comes one of the coldest details in the entire story. The lunar module was useful right up until it was not useful anymore. Once the crew and all critical materials were back inside Columbia, the LM had no further role in the return. It was jettisoned and left behind in lunar orbit. Apollo 11 discarded Eagle about 4 hours after docking. That is an extraordinary fact when you stop and feel what it means. The machine that had carried 2 human beings down to the moon and then back off the moon was thrown away because the mission had already moved on to the next layer of survival. That was not wasteful. It was the plan. Apollo was designed to drop hardware the moment that hardware stopped helping. The descent stage stayed on the lunar surface. The ascent stage reached orbit, reconnected with Columbia, and then it too became dead weight. Once its job was done, keeping it attached would only burden the next phase, so NASA let it go. The mission did not preserve hardware for sentimental reasons. It preserved only the system still needed for survival. That is why the return from the moon can be understood as a sequence of shrinking circles of safety. On the surface, the lunar module is the shelter. Once ascent begins, the safe place becomes the ascent stage. Once docking is complete, safety shifts again to the docked spacecraft together. Then after transfer and jettison, the safe place becomes only the command module and the service module. At every successful step, the number of systems that still matter gets smaller. The mission gets simpler only because each dangerous phase ends with something being abandoned. That is one of the reasons Apollo looks so clean in hindsight. When you look back, it can seem like a beautifully organised mission, moving from stage to stage with perfect logic. And it was logical, but the logic was severe. Apollo got that clean shape by cutting away everything no longer needed as soon as the next layer of survival had been secured. It is clean because it is ruthless. There is no extra machine kept around for comfort. There is no spare architecture riding along just in case. There is only the current layer of survival and then the next one. And that should change how you think about docking in lunar orbit. It was not just a technical success. It was a transfer of survival from one vehicle to another. Up to that point, Armstrong and Aldrin were still living inside the temporary part of the mission. After docking and transfer, they were back inside the part designed for the long trip home. The moon had not been defeated when they landed. It had not even been defeated when they launched off it. The moon started losing its hold when the three-man mission was physically reassembled in orbit. But even then, they still were not on their way home yet in the full sense. They were back in the right ship, yes, but they were still trapped in lunar orbit. Earth was still far away. The command module could survive re-entry, but first it had to be sent out of lunar orbit and onto the exact path that would intersect with Earth days later. And that next step had its own tension, because the burn that sent them home happened behind the moon, where Earth could not even watch. The burn that sent them home happened when Earth could not even watch, and that made it even more serious. By this point, the crew was back together in the command and service module, but they were still trapped in lunar orbit. Being in the right spacecraft did not mean they were on the way to Earth yet. To actually leave the moon, they needed one more major engine burn, and this time the job belonged to the big engine on the service module. That engine was the Service Propulsion System, usually called the SPS. It produced about 20,500 pounds of thrust, roughly 91 kilonewtons. It used hypergolic propellants, chemicals that ignite the instant they touch each other. That matters because hypergolic engines are chosen for reliability. You do not need a separate ignition system to start combustion. For a mission like Apollo, that kind of certainty was valuable. NASA had already trusted this engine to perform lunar orbit insertion, the burn that slowed the spacecraft enough to be captured by the moon. Now, the same engine had to do the opposite. It had to speed the spacecraft up again in exactly the right way so that Apollo could break out of lunar orbit and head back toward Earth. And that is the point where the crew became homeward bound in a real sense. Not after docking, not after jettisoning the lunar module, but after the trans-Earth injection burn actually worked. Until that moment, they were still only circling the moon in the right ship. After that burn, the trajectory itself would belong to Earth again. What makes this even more intense is where the burn happened. Apollo 11's trans-Earth injection started while Columbia was behind the moon, out of radio contact with Earth. That means mission control could not talk them through ignition. There was no live reassurance, no immediate correction from Houston, no real-time voice support during the critical start of the maneuver. The burn lasted about 2.5 minutes, and for that entire time the crew and the spacecraft were operationally alone. The move that committed them to the trip home began in a communications blackout caused not by failure, but by the simple geometry of the moon being in the way. That matters because it reminds you how independent Apollo still had to be, even with ground support. People often picture the missions as being guided every second by Houston, but there were moments when the crew had to execute exactly as trained with no direct help possible. This was one of those moments. The engine had to ignite, hold stable thrust, and cut off at the right time, all while the crew was behind the moon and Earth could do nothing but wait for them to come back into contact. And this was not some rough burn where you just point in the general direction of Earth and push. Trans-Earth injection had to do two precise jobs at once. First, it had to add enough energy for the spacecraft to escape lunar orbit. Second, it had to shape the trajectory so that Earth would be at the right place when Apollo arrived days later. That is the part that can be easy to say but hard to really feel. They were not firing at a stationary target. Earth was moving, The moon was moving, Apollo was moving. The burn had to place the spacecraft onto a future path through a system where every major body was already in motion. So this was not full throttle and hope, it was timing, direction, and duration all working together. If the burn was too short, Apollo might stay trapped in a bad orbit or on an inefficient path. If it was too long, the return path could shift in dangerous ways. If the direction was wrong, even slightly, the error would grow over hundreds of thousands of miles. You do not miss by a little in cislunar space. Small errors grow into very large misses. By the time you approach Earth again, the difference can be measured not in meters, but in entire regions, or in the worst case in failing to hit the right return solution at all. That is why the SPS engine mattered so much in Apollo. It was not just another engine on the spacecraft. In practical terms, it was the heavy tool, the engine NASA used when the trajectory itself had to be changed in a serious way. It handled major mid-course work. It handled lunar orbit insertion. It handled lunar departure. When Apollo needed a big mission-defining change in velocity, this was the engine expected to do it. And that creates an important thread across the whole program. One engine mounted in the service module helped connect Earth and Moon in both directions. It helped capture the mission at the Moon, and it helped release the mission from the Moon. That same engine sat in the background through much of the flight, but it was one of the central pieces of the return architecture. It is also why Apollo 13 became so frightening once the service module was crippled. When that normal SPS path was no longer available in the way NASA expected, the return plan had to change under pressure. The mission was suddenly forced to survive without the main engine normally trusted to rewrite the trajectory. And that helps explain what Apollo was really doing at this stage. The moonwalk was over, the lunar module was gone, the crew was back in the Earth return spacecraft. Now the mission had to stop being a lunar mission and become an Earth intercept mission. The SPS burn was the dividing line between those two states. Before it, they were still held by the Moon. After it, they were on a path that led back across cislunar space toward Earth. But even after a successful trans-Earth injection, the mission still was not relying on perfect aim in the simplistic sense. NASA did not trust survival to a single flawless shot. The deeper safety was built into the geometry itself, into trajectories that could help bring the crew home even when things did not go exactly as planned. And that is where the next part gets even more interesting, because Apollo did not rely only on power. It relied on geometry that could forgive mistakes. Apollo did not rely on perfect aim, and that is one of the smartest things NASA built into the mission. A lot of people picture moon missions as if everything had to be exactly perfect from the very start. One perfect launch, one perfect path, one perfect return. In reality, NASA tried to design the trajectory itself so that it could help save the crew if something later went wrong. That idea is called a free return trajectory, and it is one of the least appreciated parts of how Apollo could come home. A free return circumlunar trajectory is basically a path that loops around the Moon and naturally comes back toward Earth, even if later propulsion fails. In other words, the geometry of the flight can do part of the rescue work for you. Apollo 11's own press material described the translunar injection path that way, as a trajectory that could still bring the spacecraft back to Earth even without the normal landing sequence being completed. That is a very important point. The backup was not always a second engine or a second spacecraft. Sometimes the backup was the shape of the path itself. That tells you something very important about Apollo thinking. NASA did not just ask, how do we get there fast, or how do we get there efficiently? NASA also asked, if something goes wrong later, can the trajectory itself still help bring the crew home? That is a very different way of designing a mission. It means safety was built not only into the hardware but into the geometry. Before the landing phase really began, the mission could still be sitting on a path that naturally curved around the Moon and back toward Earth. But this is where it is important not to oversimplify it. Free return was a safety net, not a magic shield. It could protect the mission from some failures, but not from all of them. Once the crew committed to the landing sequence, separated the lunar module, changed lunar orbit, and dropped to the surface, they were no longer just riding a passive return loop. At that point, the moon had them in a more serious way. Now they needed power descent, they needed rendezvous, they needed docking. So free return helped protect the overall architecture, especially before landing. But it did not remove the danger of the surface phase. That is the key limitation. Free return was strongest before the moon landing started to break the mission into separate vehicles and separate orbits. Once Armstrong and Aldrin were on the surface, the mission could not just relax and let geometry bring them home. The surface phase still required engines, timing, guidance, and reassembly in lunar orbit. So the safety net became weaker exactly where the mission became most severe. And that makes the next point even more impressive. Apollo did not need huge constant correction burns all the way home. Once the trans-Earth injection burn had put Apollo 11 on its return path, the mission only needed one return flight mid-course correction, and the SPS burn lasted just 11.2 seconds. That is an incredibly small adjustment when you remember the scale of the mission. They were returning across roughly 250,000 miles, around 400,000 kilometers of space, and the correction needed was only a short engine firing. That number matters because it shows how accurate the earlier work had been. The translunar targeting, the lunar operations, the trans-Earth injection, the navigation, all of it had been done so well that the return path was already very close to correct. Apollo did not get home because the crew kept rescuing a bad trajectory with endless engine burns. Apollo got home because the trajectory was already nearly right, and the systems on board were good enough to trim the remaining error. That is a much more serious kind of precision than people usually picture. In movies, spaceflight often looks dramatic because engines are always firing, alarms are always sounding, and the crew is always fighting a visible crisis. Apollo's real danger was quieter than that. Most of the time, the spacecraft looked calm. The crew looked calm, the flight plan looked orderly. But underneath that calm, the math had to stay almost exactly right. The drama was hidden in numbers, timing, angles, and tiny corrections that only stayed tiny because the mission had already been flown with extraordinary discipline. And in some ways, that is more intense, not less. A loud problem at least announces itself. A quiet mission, with tiny correction burns, means the tolerances are already very tight and the planning is already doing most of the work. The calm is not proof that the danger is gone. The calm is proof that the system is balanced on precise calculations that were done correctly. That is why the return from the moon feels strange when you really look at it. It is not loud enough to match the scale of what is happening. A spacecraft has left lunar orbit, crossed cislunar space, and is now coming back toward Earth at enormous speed, and yet the visible signs of course correction are small. One short mid-course correction, a few measured updates, a mission that looks controlled because it actually is controlled. That kind of control is hard to appreciate until you realize how badly things could go wrong if the geometry had been off earlier. So Apollo's return was not built on blind hope, and it was not built on the fantasy of perfect aim in a simple sense. It was built on something smarter, a trajectory designed to be forgiving where possible, and accurate enough that only small corrections were needed later. The mission worked not because the crew kept fixing chaos, but because NASA had shaped the path so carefully from the start. And that leads to the next thing people still underestimate. If the path home was this precise, if the burns were this disciplined, and if even small errors mattered, then what kind of computer was helping manage all of this? Because the answer sounds almost ridiculous now. They navigated home with a computer that would embarrass a wristwatch. They navigated home with a computer that would embarrass a wristwatch, and that is not an exaggeration. By modern standards, the Apollo guidance computer was tiny. It had 36,864 words of fixed memory and 2,048 words of erasable memory. If you compare that to modern phones, laptops, or even ordinary smart devices, it sounds almost absurd that this machine was involved in getting people to the moon and back. But the important point is not that Apollo somehow did modern-level computing with primitive hardware. The important point is that Apollo was designed around the limits of that hardware from the beginning. NASA did not ask the onboard computer to do everything. That would have been impossible. Instead, the mission spread the work across the whole system, Some of the intelligence was in the trajectory design, some of it was in the procedures, some of it was in the astronauts themselves, some of it was in the ground tracking network, and some of it was in the computer. That is the real brilliance. Apollo did not depend on one all-knowing machine. It depended on a carefully balanced distribution of work across humans, hardware, and geometry. That matters because it changes how you should picture guidance on the way home. The spacecraft was not just blindly following one digital brain. The return was being supported by layers of information and cross-checks. The command and service module carried onboard optics, including a scanning telescope and a sextant that could be used for celestial navigation and landmark-based checks. The guidance system could process information from multiple sources, and ground tracking on Earth was still part of the larger navigation picture. So Apollo navigation was not purely digital in the modern sense, it was hybrid. That hybrid design was extremely important on the return leg. Deep space navigation is not forgiving just because you're already headed generally toward Earth. The trajectory still has to be known accurately enough to support mid-course decisions and, ultimately, atmospheric entry. If your understanding of your position, speed, or orientation starts to drift, then the risk grows later. That is why Apollo did not trust one sensor, one display, or one style of thinking. It used onboard optics, onboard computation, crew procedures, and ground-based measurements together. And that also means the astronauts were not passive passengers using a magical machine. They had to understand the system well enough to monitor it, question it, and in some cases step in when needed. Apollo crews were trained to recognize bad guidance states, watch for wrong behavior, and work through parts of the logic flow instead of treating the computer like an unquestionable authority. That is one reason AGC history still matters. The computer was not running the mission alone, the astronauts were working with it under pressure. This is where the DSKY becomes important. The DSKY, the display and keyboard unit, was not just some keypad attached to a computer. It was the interface through which the crew and the guidance system communicated. Commands were entered there, data was checked there, program states were managed there. It was one of the places where survival became a conversation between human judgment and machine calculation. Apollo return was not autonomous flight in the modern sense. It was supervised automation, and the supervision mattered. That should make you respect the system more, not less. The computer was limited, but the mission around it was structured so that the limited computer could still do meaningful, critical work. The astronauts were not expected to replace the computer. The computer was not expected to replace the astronauts. The two were expected to cooperate inside a larger mission design that had already simplified and organized the hardest parts as much as possible. And even with all of that working, precision still did not mean comfort. That is another thing people can misunderstand. A cleanly operating guidance system does not remove the stress of what the crew is actually doing. They were still in a capsule, returning from the moon at extreme speed, trusting a chain of calculations and measurements to bring them into a very narrow entry solution at Earth. The acceptable corridor for re-entry was tight enough that being just a little off could become lethal. So even when the instruments looked good and the guidance logic behaved properly, the underlying situation was still severe. That is why Apollo still feels almost unreal when you slow it down enough. The crew had to trust that a very small computer supported by optics procedures and ground tracking was helping guide them home across cislunar space toward a narrow atmospheric entry corridor. By modern standards, the onboard hardware looks weak, but Apollo shows that raw computing power is not the whole story. Good engineering is not just about having more processing. It is about structuring the problem so that the processing you do have is enough. And that is where Apollo makes modern confidence look a little childish. Today, people often assume bigger software and bigger hardware automatically mean safer or smarter systems. Apollo proves something more demanding. If the mission architecture is clean enough, if the procedures are disciplined enough, and if the humans inside the system are trained well enough, very limited hardware can still support something extraordinary. But that does not make the mission comfortable, it makes it disciplined. So by this point, the crew was on a precise return path, supported by a hybrid navigation system and a small but carefully used computer. But being on the way home did not mean the danger was fading into the background. They were still in deep space, still depending on life support, power, thermal control and consumables. In other words, the trip home was still a survival problem long before the atmosphere ever came into view. The trip home was still a life support problem, not a victory lap. Once Apollo left lunar orbit, the crew was finally headed in the right direction, but that did not mean the danger had dropped away. They were still in deep space, still days from Earth, still inside a vehicle that had to keep them alive the whole time. The space between the Moon and Earth was not empty in any practical sense. It was a long endurance test. If the systems inside the command and service module kept working, the mission could continue. If enough of them stopped working, being homebound would mean nothing. That is because the CSM was not just a cabin with some controls, it was a tightly integrated survival machine. The command module carried the crew, the seats, the controls, and the area they would actually return to Earth in. The service module carried propulsion, electrical power generation, environmental systems, and much of the support hardware needed during the coast. Those two pieces worked together as one operational unit for most of the return. So even after leaving the Moon, the astronauts were still depending on a complex system whose failures could still kill them far from Earth. And this is where spaceflight gets more unsettling the more you understand it. You do not need a huge dramatic event to die in deep space. You do not need the spacecraft to explode. You do not even need a major collision or a fire. Sometimes a return mission can fail because the chemistry of the air slowly becomes wrong. Carbon dioxide was one of those quiet threats. Apollo spacecraft used lithium hydroxide canisters to scrub carbon dioxide out of the cabin atmosphere. That sounds simple, but it is one of the most important life support jobs on the spacecraft. If exhaled carbon dioxide is not removed, it builds up. The crew does not lose air in the usual sense. Instead, the air stops being safe to breathe. That became famous during Apollo 13 because the damaged mission suddenly turned a background system into a life or death crisis. NASA had to improvise a way to use command module carbon dioxide canisters inside the lunar module because the systems were not originally meant to fit together that way. And that story matters far beyond Apollo 13 itself, because it teaches the real lesson of return flight. Space does not need a spectacular accident to kill you. It can kill you slowly through air chemistry, power loss, thermal imbalance, or the steady failure of systems people barely think about when everything's working. Apollo 13 is the clearest proof that the return architecture had hidden strength, but also that those strengths were not unlimited. After the service module explosion, the mission did not follow the normal return plan. The lunar module had to become a lifeboat. That word is not dramatic language added later. It is exactly what it became. The LM, which had been designed for a lunar landing, suddenly became the place that kept the crew alive during a crisis. The spacecraft built for one part of the mission had to temporarily support another part of the mission because the original system had been damaged. And that is why Apollo's design was more resilient than it first appears. It was not elegant because it was simple. In fact, it was not simple at all. It was elegant because the pieces could sometimes take over for one another in an emergency, without the whole mission instantly collapsing. Apollo 13 proved that the modular design had room to bend under pressure. It could absorb a major disaster and still preserve a road home. But Apollo 13 also proved the limit of that strength. The system did not absorb the failure comfortably. It absorbed it barely. That distinction matters. When people hear that Apollo 13 got home, they can accidentally hear that as proof the system was robust in some easy, forgiving way. It was not. The return worked because the architecture had enough depth to support desperate improvisation, and because the crew and ground teams managed the crisis with extreme discipline. The mission survived because Apollo had been built with separate pieces and backup logic. But those pieces were stretched into roles they were never meant to play for so long. That is not softness, that is narrow survival. And that brings you back to the normal return coast, which can look calm only because successful missions hide their own fragility. On a mission like Apollo 11, after trans-Earth injection, the spacecraft is on the right path, the systems are stable, and the timeline looks orderly. From the outside, it can seem like the hard part is over, but from inside the mission, the crew is still depending on life support, power, thermal control, attitude control, and trajectory control, and all of those things remain linked. A problem in one area can spread into another. Power affects heating. Heating affects equipment performance. Attitude affects thermal conditions and communications. Propulsion capability affects how much correction authority remains if something drifts. Nothing is really isolated. So coming home was still conditional until the very end. As long as the crew was still in cislunar space, survival depended on consumables and margins. Oxygen, electrical power, water, carbon dioxide scrubbing, orientation and guidance all remained active concerns. The spacecraft had to keep functioning as an ecosystem and as a vehicle at the same time. The return only looks peaceful because the successful missions made that constant systems management seem invisible. That is one of the hardest truths about Apollo to feel properly. Even after the moon was behind them, even after the big burn had been completed, even after the path home had been established, the crew still was not guaranteed survival. They were still in the long middle part of the mission where nothing dramatic might happen, and that itself is dangerous because it can make the machinery of survival seem automatic. It was never automatic. It was maintained, monitored, and rationed. So the return from the moon was still not a simple ride back. It was a controlled endurance problem, one the spacecraft had to solve hour after hour, until Earth finally became close enough to matter again. And when Earth did come back into the picture, it did not offer safety immediately. It offered a new problem, one of the most severe in the whole mission, because getting home meant entering the atmosphere through a corridor so narrow that being a little wrong could still kill you. Earth return was not a dive, it was a very narrow atmospheric negotiation, and that is the part people often underestimate. By the time Apollo came back from the moon, the crew had already survived launch, lunar landing, ascent, rendezvous, docking, and the trip through cislunar space. But none of that guaranteed they could actually get through Earth's atmosphere alive. Re-entry was its own problem, and it started much earlier than most people think. For Apollo, NASA treated the entry interface as about 400,000 feet above Earth, roughly 122 kilometers. That is far above clouds, far above what most people would casually call the real atmosphere, but it is where atmospheric capture starts to matter for a spacecraft coming in that fast. From that point on, the command module had to start getting rid of an enormous amount of energy. And that is the key idea. Re-entry was not just falling down toward Earth, it was controlled energy disposal. The spacecraft had to use the atmosphere to bleed off speed without letting heating, deceleration, or trajectory errors become fatal. That is why the entry corridor mattered so much. If Apollo came in too shallow, the command module could skip back out of the atmosphere at very high speed and miss the landing solution. If it came in too steep, the aerodynamic loads and heating would rise too far and too fast. So this was not a case where any downward path would do. The spacecraft had to hit a narrow band of acceptable conditions. And NASA was not only thinking about survival in a basic sense. Apollo also had a range requirement of about 2,500 nautical miles, around 4,630 kilometers, partly so the landing point could be managed and bad recovery weather could be avoided. That means the atmosphere was not treated like a passive cushion, it was treated like a guided medium. That is the part that makes Apollo feel much more advanced than the usual public memory. People remember a capsule coming back and then parachutes opening, but before the parachutes, the command module had to act like a controlled hypersonic vehicle. It was not just dropping, it was flying in a limited but very real sense. And that only worked because the command module was not a perfect symmetric shape. If Apollo had been a pure blunt object with no useful lift, it would have had much less control over the path through the atmosphere. NASA's entry documentation shows that the command module had an offset center of gravity. That gave it a lift-to-drag ratio of about 0.30 in Apollo 11 entry data. That sounds small, and in everyday flight it would sound almost meaningless. But at re-entry speeds, even small lift matters a lot. That tiny amount of lift meant the capsule could be steered. By rolling the command module and changing the direction of that lift, Apollo could manage its path, shape its cross range, and stay inside the right corridor. It did not just tumble like a meteor and hope the atmosphere would sort things out. It used controlled roll and an intentionally asymmetric design to make the atmosphere work for it instead of simply suffering whatever the atmosphere did next. That is a huge difference. A meteor survives nothing. It just comes in and burns or impacts. Apollo had to survive because it could guide the violence. It had to use the atmosphere to slow down, but use it in a controlled way. Too much deceleration in the wrong profile and the crew could be injured or worse. Too much heating in the wrong path and the thermal protection problem gets harder. Too little capture and the capsule can skip back out. So everything about entry was a balancing act: speed, angle, lift, heating, load, and landing geometry. And this is where the sophistication of Apollo really shows. The public story often makes it sound primitive because the spacecraft looks like a simple cone-shaped capsule. But the real story is much more technical than that. This was a vehicle coming back from the moon at extreme speed, using a very carefully chosen shape, an offset center of gravity, and controlled roll commands to carve out a survivable path through the atmosphere. That is not crude early spaceflight, that is serious flight dynamics. It's also one of the reasons the return home stayed dangerous so late in the mission. By this point, the astronauts could be hours away from splashdown and still one bad entry profile away from disaster. A lot of people think of re-entry as the final descent, almost automatic once the spacecraft reaches Earth. Apollo shows the opposite. Earth itself becomes the next hazard. The atmosphere is the only thing that can slow the spacecraft enough to save the crew, and at the same time, it is the thing that can destroy the spacecraft if they arrive the wrong way. So even after days in deep space, even after all the navigation and all the successful systems work, the crew still had to trust that the command module would enter the atmosphere on the correct path and that its flight behavior would stay inside the narrow envelope NASA had planned for. This was not a forgiving phase. It was another point where precision mattered more than force. And the really unsettling part is how little this resembles the popular image of just plunging down through the sky. Apollo was not diving at Earth like a falling object. It was arriving as a guided hypersonic capsule with just enough lift and just enough control authority to manage a survivable entry from lunar return speed. That is a much more exact and much more difficult thing than most people picture. So when people reduce the return to they came back and splashed down, they skip one of the most demanding parts of the mission. Before the parachutes, before the ocean, before recovery, Apollo had to get through a section of atmosphere where the spacecraft was still moving so fast that even small mistakes in angle or control could be fatal. That is why the return was not really a descent. It was a negotiation with physics, inside a corridor so narrow that success depended on the vehicle behaving like a guided system all the way through. And that leads straight into the next part, because once you understand how precise entry had to be, the speed becomes even more shocking. Apollo was not just coming home fast. It was hitting Earth's atmosphere at speed so high that the air itself turned into one of the main threats. They hit Earth's atmosphere at speeds that turn air into an enemy. Apollo 11 came in at about 39,000 kilometers per hour, around 24,000 miles per hour. That is why a return from the moon is not the same as coming down from low Earth orbit. Low Earth orbit re-entry is already violent. A lunar return is worse because the spacecraft is bringing in much more energy. So this was not a gentle trip home. The crew had to use Earth's atmosphere as a braking system against a speed so high that the atmosphere itself could become deadly. That is the first thing to understand about this phase. The danger was not just the spacecraft moving fast. The danger was what happened when that speed met air. At lunar return speed, the atmosphere is not some soft blanket waiting to catch you. It becomes a harsh physical environment almost instantly. The spacecraft has to lose an enormous amount of energy in a short period of time, and all of that energy has to go somewhere. A lot of it turns into heat. A lot of it turns into extreme aerodynamic stress. So the return to Earth was not simply a descent. It was a controlled collision with the upper atmosphere. and that is why the heat shield mattered so much. A lot of people think a heat shield works by just blocking heat like a wall. Apollo's did not work that way. It worked by sacrificing itself. The command module used avcoat, an ablative material designed to char, erode, and break down in a controlled way during re-entry. NASA and Smithsonian descriptions of Apollo-class entry put the heat shield environment at around 5,000 degrees Fahrenheit, about 2,760 degrees Celsius. At those temperatures, the goal is not to stay untouched. The goal is to let the shield take damage in a very specific way so that the crew cabin underneath survives. That is one of the most important ideas in the whole return story. The heat shield was not trying to remain perfect. It was designed to be consumed correctly. Material would burn, char, and carry heat away from the structure. In other words, the shield protected the crew by dying in a controlled way. That is not a side detail. That is the reason the command module could come back from lunar speed without turning the cabin into an oven. And once you understand that, the visual side of re-entry starts to make more sense. As Columbia came in, it did not just get hot in some abstract technical way. It became surrounded by superheated ionized gas, the glowing plasma people associate with meteors and fireballs. That bright sheath was not added drama. It was the visible result of air being compressed and heated so intensely around a spacecraft arriving from another world. So when Apollo hit the atmosphere, Earth's air became two things at the same time. It became the only thing that could slow the capsule enough for the crew to live. And it became one of the main threats trying to destroy the capsule during that process. That is the physical paradox at the center of the return. The astronauts had to hit the atmosphere hard enough to be captured and slowed down, but not so hard that the heating and deceleration went past safe limits. They needed friction, but only in the right amount and in the right profile. Too little atmospheric capture, and the return could fail. Too much in the wrong way, and the spacecraft could be overwhelmed. So even at this late stage, after all the major burns and all the navigation work, survival still depended on managing a very narrow balance. This is why getting home from the moon is such a misleadingly simple phrase. It sounds like the danger should be fading by now. In reality, Apollo was entering one of the harshest environments of the entire mission. The spacecraft had already crossed deep space successfully, but now it had to survive a return speed so high that the air around it turned into a destructive medium. And the only reason that became survivable was because NASA had designed the command module, the heat shield, and the entry profile to work together as one system. So the return at this stage was not about comfort, and it was not about momentum carrying them safely the rest of the way. It was about controlled punishment. The heat shield had to erode correctly. The trajectory had to stay inside limits. The structure had to survive. The crew had to tolerate the deceleration. The atmosphere had to slow them down without winning completely. That is the brutal trade at the center of lunar return. The same air that makes Earth livable becomes dangerous when you hit it from the moon. And that tension is what makes this phase feel so severe even today. Apollo had escaped the moon, rebuilt the mission in orbit, crossed cislunar space and reached Earth. But Earth was not simply welcoming them back. It was forcing them through a test where every second of successful slowing came from conditions that could also destroy them. That is why the return does not really get easier here. It just changes form. And then, right in the middle of that violence came one of the loneliest parts of the whole mission. Because the plasma around the spacecraft did not only glow, it could also cut them off from radio contact. In other words, during one of the most dangerous parts of the return, the crew could disappear into silence. Then came the blackout, and this was the worst silence in the mission. The plasma around the command module did not just glow, it could interfere with radio communication. During the hottest part of re-entry, the ionized gas around the spacecraft could disrupt the signal between the crew and the ground. That means one of the most dangerous phases of the entire return included a period when mission control might not be able to hear the astronauts, and the astronauts might not be able to hear mission control. So at the exact point when the spacecraft was under extreme heat and deceleration, the crew also had to pass through a stretch of isolation. That is a serious detail, because it changes the emotional feel of re-entry. People often picture Houston guiding every part of the mission in real time, with a constant voice loop holding everything together. But blackout interrupted that. During those minutes, the normal pattern of communication could drop away. The crew had to keep moving through entry without the reassurance of immediate contact. Apollo's most violent part was also one of its loneliest, and this was not some theoretical issue engineers worried about in advance and then never really faced. NASA had already documented blackout effects during Apollo re-entry testing. Communications behavior and radar performance under plasma conditions was studied carefully because this was a known feature of returning through the atmosphere at those speeds. In other words, blackout was not a dramatic flourish added later to make the story sound more intense. It was an operational reality of lunar return flight. The spacecraft had to be designed and flown with the expectation that for part of entry, the outside world would effectively go quiet. That matters because blackout itself was not the main danger. Losing radio for a short time does not automatically kill the mission. The real danger was what blackout meant in context. It meant that during one of the harshest phases of the return, the crew could not depend on immediate ground support. They had to trust that the guidance was right, that the entry profile was right, that the systems were healthy, and that their training was enough to tell them if something was drifting into trouble. So the frightening part was not just silence by itself. The frightening part was needing everything else to already be correct while the silence lasted. This is exactly why Apollo's entry guidance mattered so much. By the time blackout arrived, the mission could not be relying on voice reassurance from Earth to hold itself together. It had to rely on prior calculations, onboard logic, vehicle stability, and disciplined crew monitoring. The astronauts were not being carried through that phase by conversation. They were being carried through it by the correctness of everything that had been set up before the blackout began. And that also shows why Apollo training had to go beyond simple procedure following. The crew needed to understand what the spacecraft should be doing, how it should feel, what the instruments should show, and what signs would suggest something was wrong. During blackout, there is no emotional relief from hearing calm voices on the ground. There is only the vehicle, the instruments, the physics, and the crew's ability to recognize whether the mission is still inside its planned envelope. That makes blackout one of the starkest moments in the whole return story. A spacecraft is coming back from the moon, wrapped in ionized gas, passing through an entry corridor only a few degrees wide, under severe heat and deceleration, and for part of that descent it effectively disappears into controlled silence. That stops feeling like ordinary transportation very quickly. It becomes something much more severe. The spacecraft is no longer just travelling. It is surviving an environment where even communication is temporarily taken away. And this is one of the reasons Apollo Return still feels so unreal when you break it down step by step. The mission had already solved so many enormous problems by this point, but it still had to pass through a phase where no one on Earth could necessarily help in real time. The command module had to stay stable, the guidance had to keep doing its job, the crew had to hold trust in systems they could not step outside and inspect. The silence was built into the physics of the return. So blackout is not just a communications detail. It is one of the clearest examples of how Apollo forced human beings to trust a machine and a plan under conditions that were beyond normal human experience. The capsule was not just descending through air. It was passing through a state where the atmosphere itself became both shield, threat, and temporary wall between the crew and Earth. And once that silence ended, the mission still was not finished. The capsule still had to slow from lunar return violence to a water impact human bodies could survive. That final step sounds almost simple compared with everything before it, but it required another precisely layered system. Because after all the heat, plasma, and blackout, parachutes still had to do one last impossible thing. Then the parachutes had to do the final impossible thing. They had to turn a return from the moon into a water landing a human body could survive. By the time the command module reached this stage, it had already gone from about 39,000 kilometers per hour, around 24,000 miles per hour, through atmospheric entry, heating, plasma, guidance, and blackout. Now it had to slow all the way down to an impact speed of around 20 miles per hour, about 32 kilometers per hour. That is still not soft. Hitting the ocean at that speed is serious, but compared with lunar return speed, it is an almost unbelievable reduction. And it did not happen through one big heroic parachute opening at the last second. It happened through a carefully staged system built to slow the capsule down without tearing it apart. That stage sequence is important because the loads involved were too high to handle carelessly. Apollo used 2 drogue parachutes, each 16.5 feet across, about 5.0 meters, for the first part of stabilization and deceleration. Their job was not to finish the landing. Their job was to help get the capsule under control, reduce speed further, and set up the next phase. Then came 3 pilot chutes, which pulled out the 3 main parachutes. Those main chutes were huge, 83.5 feet across each, about 25.5 meters, and even that was not just a simple full opening. The main parachutes used a reef deployment sequence, which means they opened in stages, rather than snapping fully open all at once. That was done to keep the forces from becoming destructive. So the parachute system was layered on purpose, first stabilization, then extraction, then controlled full deceleration. NASA notes that the drogues remained attached until around 11,000 feet, and only after that did the mains fully take over. That tells you how seriously the final descent was engineered. This was not a single canopy saving the day. It was a chain, just like the rest of Apollo return. Every STI handed the spacecraft to the next stage under tighter control, and even after that, splashdown itself was not treated like a random ocean impact. The command module did not just fall straight into the water in any orientation. Smithsonian documentation notes that under the main parachutes, the capsule was held at about 27.5 degrees. That meant the slanted side of the command module would hit the water first, which reduced the force of impact. That detail matters because Apollo did not merely need to land somewhere in the ocean, it needed to hit the ocean in a way the structure and the crew could tolerate after everything that had already happened. Even the angle of the water strike was part of the design. That is one more reason the return feels so exact when you break it down. The parachutes were not just slowing the spacecraft, they were managing the final geometry of survival. The capsule had to arrive under control, in the right attitude, at the right speed, and in the right place. The ocean was not simply the end of the mission. It was one more environment Apollo had to negotiate correctly. And Apollo 11 shows just how exact that whole chain was. The parachutes deployed at 195 hours, 13 minutes into the mission. Splashdown came at 195 hours, 18 minutes, 35 seconds. That is only a few minutes from parachute deployment to final impact, but inside those minutes, the whole landing sequence had to work exactly as planned. Apollo 11 came down about 30 miles from USS Hornet, the recovery ship. That closeness matters, because this final step was still navigation. After every burn, every orbit, every correction, every entry constraint, the mission still had to hit the Pacific in the right area, so recovery could happen quickly and safely. And there is another detail that makes this even more impressive. Because of bad weather, the landing point had already been shifted by about 250 miles, around 400 kilometers. So even near the very end, the mission was still adapting to conditions and still aiming for a controlled solution, not just any solution. That means the last act of getting home was still technical, still planned, still precise, survive the atmosphere, deploy the parachutes correctly, hit the water at the right speed and angle, and do it near the right ship. That is what makes the end of Apollo so different from the simplified public memory. People remember the ocean landing as the calm part, the part where the danger is basically over. But the parachute phase was still doing serious work. The system had to survive deployment loads, the mains had to open properly, the capsule had to stay stable, the final attitude had to be right, the recovery area had to be correct. Apollo did not simply fall into the ocean and get lucky, it completed one more tightly engineered sequence. And that makes the full return even harder to dismiss as just a successful trip back. The spacecraft had gone from lunar return speed to a survivable splashdown through a long chain of controlled transitions. Boost, capture, orbit, rendezvous, docking, departure, coast, re-entry, blackout, parachutes, splashdown, recovery. The parachutes were the final system in that chain, and they had to turn all the remaining violence into something a human body could survive. But even here, the story still points to a bigger conclusion. If you step back and look at the entire return, what stands out most is how little room for error there really was. The whole chain worked, but it worked inside margins that were often brutally small. And that is the last thing you need to feel before the story is complete. Because the reason Apollo return still sounds unbelievable is simple. There was almost no room for anything to go wrong. The reason this still feels unbelievable is that there was almost no room for error. Once you strip away the famous images and the familiar story, the return from the moon starts to look much harsher. It was not forgiving. It was not robust in the modern sense where you assume another vehicle can be launched or a rescue can be attempted. Apollo was robust in a narrower and more serious way. Every critical step was studied, tested, and engineered so it would work the first time, because in most cases there was no useful second chance. The darkest example is the ascent engine. If that engine failed on the moon, the mission ended there. There was no practical surface rescue. There was no backup lander coming over the horizon. There was no way for Michael Collins, circling above in Columbia, to come down and collect Armstrong and Aldrin. The entire return chain assumed that the ascent stage would ignite and perform as planned. That is why NASA treated ascent guidance, backup logic, rendezvous timing, and orbit phasing with such extreme seriousness. Those were not fine details. Those were the difference between a successful return and two astronauts being stranded on another world. And that is what makes Apollo harder to absorb once you stop thinking about it as the triumphal story and start thinking about it as an engineering system. People often hear they landed on the moon and feel that as the impossible part. But in survival terms, the mission still had one of its coldest dependencies ahead of it. The engine had to light. It had to push the ascent stage into the right orbit. The timing had to work, the guidance had to work, and none of that could be softened by rescue options if it failed. But even a successful ascent did not guarantee survival. That is the next uncomfortable truth. If Rendezvous failed, Earth was still out of reach. Armstrong and Aldrin could launch off the moon perfectly, and still die if they could not reconnect with Columbia. The lunar module ascent stage was not built to survive Earth re-entry. It was never supposed to. It was built to lift them from the lunar surface and get them back into orbit. That means leaving the moon solved only one impossible problem. It did not solve the whole return. That is what makes Apollo return so unnerving when you look at it without nostalgia. The mission was a chain of hard dependencies. Launch from the moon, reach the right orbit, reconnect with the command module, transfer back into the return ship, leave lunar orbit, hold the trajectory, survive re-entry, deploy parachutes, splash down in the right place. If any one of those gates failed badly enough, the mission could still end in disaster. The success of Apollo can make that chain look smooth, but smooth is not the same as safe. And that is why Apollo 13 matters so much in this story. Apollo 13 is the proof that the architecture had real hidden strength. When the service module explosion destroyed the normal return path, the mission still found a way home by using the broader structure NASA had built into Apollo. Loop around the moon, preserve the trajectory, use the lunar module as a lifeboat, improvise life support, manage guidance under terrible conditions, still hit the entry corridor at Earth. NASA's own records describe the LM as a lifeboat. And that word matters. It means the architecture had enough flexibility to bend under catastrophic failure and still preserve a path home. But even that should not be misunderstood. Apollo 13 does not prove the system was casually resilient. It proves the system had depth. There is a difference. It could bend without snapping immediately, but it bent under extreme stress. The crew survived because the mission architecture gave them something to work with, and because both the astronauts and the ground teams used that architecture with extraordinary discipline. Apollo's greatest return innovation was not just that it could reach the moon, it was that even after major damage, it could still sometimes find a road home. So when you ask how they got home from the moon, the real answer is that they never treated home as one event. They treated it as a sequence. First, they escaped the lunar surface. Then they rebuilt the mission in orbit. Then they found the command module. Then they used the big engine behind the moon to begin the trip back. Then they followed a tightly controlled path across cislunar space. Then they hit Earth's atmosphere at about 39,000 kilometers per hour, around 24,000 miles per hour, inside a narrow entry corridor. Then the heat shield sacrificed itself correctly. Then the guidance carried them through a blackout. Then the parachutes turned that return into a survivable splashdown. That is the full answer. Apollo did not get home by brute force, and it did not get home through one single heroic move. It got home because NASA broke the return problem into smaller survival problems and solved every one of them before the crew ever launched. One spacecraft for the moon, one spacecraft for Earth return, one ascent engine to escape the surface, one rendezvous plan to rebuild the mission in orbit, one major burn to leave the moon, one carefully shaped trajectory, one controlled atmospheric entry, one layered parachute system. Every stage had its job and every stage had to work, and that's why the story still feels almost unreal. Not because it was magic, and not because people back then ignored the risks. It feels unreal because the mission accepted just how hard the return was, and then designed around that fact with extreme precision. They did not get home by pretending the moon was just another destination. They got home by treating it as a place that could keep them, and by building a mission that could escape it step by step. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.